This is the ELEC 1510 Logic Design Lecture 5, Video 1 on canonical forms corresponding to textbook section 2.6. So when we talk about canonical forms, there are two main forms that we talk about, what are called min terms, which leads to something called SOP form for sum of products, and less often used are max terms, which lead to something called POS form, which is product of sums. So mostly I'm going to be talking about min terms this time around. I'll briefly talk about max terms, and then we'll be using these for basically the whole rest of the class to define logic circuits and truth tables. All right, so let's begin with a function, the AND function, a very simple function. I have what looks like the simple function here, z equals x and y, and then a truth table. And I'll fill in this truth table. We know that z is only going to be a 1 when both of the inputs are a 1, so there's only one row. Now, I can just write this as the expression that I've seen here, or if I am only given a truth table, I can look at this and see that every single row in the truth table is a different collection of input states. The very first state would be when the inputs are x prime, y prime, for x equals 0 and y equals 0. So if z had been a 1 there, I could have said that z was equal to x prime, y prime. Now the second row is x prime, y. The third row is xy prime. And the fourth row is xy. So in a row, whenever a variable is a 0, it is primed in the expression, and whenever a variable is a 1, it's not primed. So we have all four of these inputs, and then the output here can just be said to be a sum of whatever set of inputs makes the output true based on the truth table. There's only one set of inputs that makes the output true, it's this one. So z in this case is equal to just x, y. All right, so that's a pretty simple case. Now let's move on to one that's slightly more complicated in this method of thinking about it, the OR function, z equals x or y. So now we already know that the output is going to be a 1 whenever one or more of the inputs is a 1. So now I can fill in the various states that have to do with each row in the truth table, x prime, y prime, x prime, y, x, and xy. So now z is going to be a 1 whenever three of these conditions are true, x prime y, xy prime, and xy. So in its most expanded possible form, z is equal to x prime y plus or xy prime or xy. So because z has three conditions that make it a 1, it has three possible input states that we OR together to get the full output. Now this can be simplified by seeing that we can factor out of the second expression in x to get y or y prime, and that becomes a 1. And then this is one of those forms where we use the distributive theorem to get rid of the x prime, so eventually z just equals x or y. Okay, so then we've simplified it back into this form, but the expanded form looked like this. And this is what we would call the sum of products form, which is not usually the most efficient form for representing your function. Usually it can be simplified from the sum of products form. And then each one of these terms, x prime y, xy prime, and xy, are what we would call min terms, because min terms are associated with a single row in the truth table. Okay, so now let's do an example just talking about min terms without a function. So the way that we write logic functions in terms of minterms is using this summation notation. So we would say that z as a function of w, x, and y is the sum of minterms 1, 3, and 6. So what that means then is that every row in this truth table, where we have inputs w, x, and y, and output z, is going to be associated with a numbered minterm. So 0, 0, 0 here is minterm number 0, 0, 0, 1 is minterm number 1, and then it goes all the way up to minterm number 7. If you have 4 variables, you can get up to minterm 15. So the sum here, sum of 1, 3, and 6, means that the output is the sum of those minterms, so it's a 1 whenever any of those minterms is a 1. So it was 1, 3, and 6, and then the rest of these are 0. All right, so we have now translated our minterm summation into the output of the truth table. And now I can write this out in sum of products form by seeing that I can write out every row just in terms of variables. Again, whenever there's a 0 for the variable in the row, that variable is primed. Whenever there's a 1, the variable is not primed. So this one, the very first one, has 0, 0, 1, so that's w prime, x prime, y. The second one right here has 0, 1, 1, so that's w prime, x, y. And then the very last row is 1, 1, 0, so that's w, x, y prime. So in total, the sum of products form for this expression is z is equal to w prime, x prime, y, or w prime, x, y, or w, x, y prime. And then this is the sum of products form. Again, it's not optimized, so this could be algebraically simplified somewhat, but if you're looking for the sum of products form or the minterm form, that is what it's going to look like for this function. Okay, max terms are essentially the complement of minterms, and they're a little bit more complicated. So max terms lead to something called product of sums form. And basically what you have to do is work with the opposite of minterms. So here I have a function wxy and then the output in terms of z, and I'm going to write out z prime, which is just the complement of z, 0, 0, 1, 0, 0, 0, 0, 1. And each of these rows, the ones that are a 1, I mean every row has a minterm associated with it, but the ones that are 1s here are minterm 2 and minterm 7, which are w prime, x, y prime, and w, x, y. So z prime in terms of the minterm expression is w prime, x, y prime, or w, x, y. But I don't want z prime, I want z, so I have to prime both sides of this expression. So z double prime, which cancels out and just becomes z, is equal to w prime, x, y prime, or w, x, y prime. And now I apply De Morgan's theorem, so z is equal to w prime, x, y prime, prime, and w, x, y, parentheses, prime. Apply De Morgan's theorem again to both of those parentheses expressions, and I will get w or x prime or y, and w prime or x prime or y prime. And so this is the product of sums form of z, which is equivalent, if you factor that out and simplify everything, to the sum of products form. But it's just written in a different way. And so that's how you go from the truth table to the product of sums form. Each one of these parentheses with a sum of literals is called a max term. Let's look at coming up with an expression for a function now just based on its max terms. So I have a function here, z of w, x, and y is equal to, now we use a capital pi for the max term expansion. Pi means multiplication, so that means product of sums, and 1, 3, and 6. Now instead of writing 1s for the 1, 3, and 6 terms, we write 0s for the max term expression. So 1 is here, 3 is here, and 6 is here. So then fill in 1s. Okay, now every single row in this truth table has a max term associated with it. For the min terms, whenever we had a 0 for a variable in a row, we used the complement of that variable, but for a max term, we don't use the complement. So a 0 would lead to just w, and a 1 in this row would lead to y prime. So then the x is just x. And then we add those together. So the max term associated with the second row is w or x or y prime. The max term associated with the fourth row is w or x prime or y prime. And the min term associated with the seventh row here is w prime or x prime or y. So then the product of sums form for this expression, z is equal to the multiplication of all of those max terms, w or x or y prime, and w or x prime or y prime, and w prime or x prime or y. All right, so there we go. That is how you analyze min terms and max terms in logical expressions and truth tables.